All right, so next thing we got to talk about here is heat capacity. And heat capacity is something that we'll learn in Science 10, but you won't use again till Chem 30 if you take Chem 30. Okay, but it's related to one of the factors affecting climate, and that's why we're kind of going over it in Science 10s. It's more related to why your climate is more moderate if you live near the ocean. Okay, water has a very high specific heat capacity. Okay, that means that it can absorb a lot of energy or give off a lot of energy without changing temperature very much. Okay, something with a low heat capacity will change its temperature very quickly with very small inputs of energy. Okay, typically metals have low heat capacities, which is why we typically make cookware out of them. All right, we make pots and pans out of metals because we don't have to put in a lot of energy to make them get hot. Okay, the energy kind of transfers through them quickly and gets into whatever is in the pan instead of using a bunch of energy to make the pan get hot. All right, with water, okay, water you can keep adding energy, and it heats up very, very slowly. Okay. Sometimes, but it's not a hard and fast rule. Insulators don't always have a high heat capacity. It doesn't hurt. The thing with the insulators are more about heat transfer as opposed to heat capacity. Okay, so something could be a good insulator and get hot itself, right? It's more about the transference or the conduction of heat, right? But yeah, generally speaking, things with a high heat capacity are generally decent insulators. Okay, the worry would be if it's got a high heat capacity, it could absorb a lot of the energy from what you're trying to insulate without changing its temperature very much, but that could change the temperature of the thing inside, right? So if I have like a cup and I've got nice hot coffee in it or something like that, but I put around it a material that has a high heat capacity that's a lot lower in temperature, the energy is still going to flow into that insulator, right? And that's not what I want. I don't want the energy to flow away from the thing I'm trying to insulate. Okay, so insulation is more about transfer as opposed to heat capacity itself. All right, so there's two different kind of types of heat capacity. There's specific heat capacity, which we're talking about if we're talking about a single substance. Okay, so if we've got a block of iron or a bunch of water or something like that. Heat capacity is if I have a object that's made of many materials. I would be talking about its general overall heat capacity, especially if it's a mixture of things. Okay, we basically never use this. Okay, we're always dealing with a single material, okay, in this course. Okay, so specific heat capacity is the amount of heat, so in joules, required to raise the temperature of 1 gram of a material by 1 degree Celsius. Okay, so how much energy is needed to warm 1 gram of a material up by 1 degree Celsius? Okay, to give you an idea, for water, that number is 4.2 joules per gram degree Celsius. Okay, so 4.2 joules to make 1 milliliter of water changes temperature by 1 degree. That's a fairly high heat capacity, right? By comparison, most metals are like in the decimals. They're like point something. Okay, much lower heat capacity, so they heat up very quickly. Right. Okay, so our units for heat capacity, for specific heat capacity, are joules per gram degree Celsius because it's the amount of energy needed for 1 gram by 1 degree. Okay, so joules per gram degree Celsius are the units. Never, because Fahrenheit is imperial and we don't use that. Okay, so always be Celsius. What's that? Civilian population, yes. Scientific, not so much. Military is even metric for the most part. Yeah. All right, so a formula can be used to find the energy needed to heat 1 gram of a specific substance by 1 degree Celsius, but the formula is really, really easy. Okay, so to calculate the amount of energy needed to heat something up, we multiply the mass of the material by the specific heat capacity by the amount we want to change the temperature. Okay, so M is mass in grams, sorry. C is the specific heat capacity. So if it was water, it'd be 4.2. Okay, and then delta T is the change in temperature. Notice it's a capital T, not a little t. Little t stands for time, right? So this stands for temperature. Okay, so this is an easy formula to manipulate. If I want to solve for anything other than energy, what do I do with the other two things? Just divide them over to the other side. Okay, so if I want to solve for M, I just divide C delta T over here. Everybody with me there? Okay. Now, where are you going to get C from? C is your specific heat capacity. I will give it to you. Okay. You have a chart in your notes package, I believe, or maybe it's in the digital workbook. It's in one of those two places. There's a chart with the different specific heat capacities. Must be in the, yeah, it's in the digital workbook, I think. All right, but there'll be a chart there, okay, or I'll give it to you or something like that. Okay, so it's not, it's unless the question says solve for the specific heat capacity, then you would just solve for it. Okay, but otherwise it would be given to you. All right, questions on how that works? Relatively easy formula. Okay, the thing we need to understand is what is specific heat capacity? It's how much energy is required to heat something, 1 gram of something by 1 degree Celsius. Okay. All right, so I'm going to go over a couple of examples here, and then I'll have you guys try a couple. This is not something that is going to tax your mathematical abilities in any way, shape, or form. Okay, it's very easy stuff. Okay, so first one here, how much heat, that is energy, is needed to raise the temperature of 150 grams, so they gave me mass, and notice we're back to chemistry now, because mass is in grams, okay, of water, whose heat capacity is 4.2 joules per gram degree Celsius, so that's C. Okay, from 5 degrees to 85 degrees. So what's my temperature change? 80 degrees. That's where people screw up. If they're going to make a mistake, it's in the temperature change. Okay, which is odd, but okay, it happens. Okay, a lot of times people just look at the biggest number and just go with that instead of looking at, oh, well, it's the change from 5 to 85 isn't 85, it's 80. Okay, so, all right, so I've got those things and I'm looking for energy. So E equals MC delta T, so that's 150 grams times 4.2 joules per gram degree Celsius times 80 degrees Celsius. All right, so the grams are going to cancel, the degrees Celsius is going to cancel, and I'll be left with joules. All right. Okay, so that's going to take 50,400 joules. Is that a lot? Yeah, it's a lot. Okay, is that one very difficult? Yep, but like I said, the manipulation's easy. Whatever you're looking for, divide the other two things over, right? Okay, try that one. I'll give you a minute on that one. Okay, so the question tells me we're looking for what material this thing is made out of. The only way to figure out what material it's made out of is to find the specific heat capacity because it's specific to each material. Okay, so I'm going to solve for C. They tell me that the mass of the cup is 100 grams. Okay, and that it takes 400 joules of energy to warm it from 12 to 62 degrees. Sorry, 4,200. Okay, from 12 to 62, which is a temperature change of 50. Okay, so I'm looking for C, and this is the formula I'm going to be using. E equals MC delta T. So since all three of these things are being multiplied together, if I want to move anything over to this side, I have to do the opposite, which is divide. All right, so I'm going to divide both sides by M delta T. Now I'm solving for C. Plug in my numbers, 4,200 joules divided by 100 times 50. Now, thing you need to keep in mind here, bottom's got to be in brackets. You don't put the bottom in brackets, it's going to do order of operations left to right. You're not going to get the same answer. Okay. So 4,200 divided by 100 times 50. All right, so I'm getting 0.84 as my answer. Now that's 0.84 joules per gram degree Celsius. Okay, because I divided joules by grams times degrees Celsius. Okay, that's the units for specific heat. All right, so now if I go back to my list, that's not where my list is. Okay, yeah, it's made out of glass, 0.840.
What if you got like 0.130 because there's two things?
Yeah, I would not give you one that came out to, it could be this or that. Yeah, because you're right. There are two things. It's actually, this is like 0.131 and this is like 0.1298 or something. Like they're close, but they're rounded off. They just happen to round to like the same thing, right?
Is that why people thought you could turn lead into gold?
No, they just thought that because they were wrong. Yeah. But that's different. That's malleability. That's a different physical property. Yeah. Okay. By the same token, one of these melts at a lower temperature than the other as well, because melting point is a characteristic physical property as well. Right? Nope. Melting point is independent of heat capacity. I mean, look at it. Water has an incredibly high heat capacity, but it melts at 0 degrees Celsius. This has an incredibly low heat capacity, but doesn't melt for several hundred degrees. Right? It's totally independent. And now you look at, let's say, hydrogen, because hydrogen's on this list, right? Hydrogen gas has got a heat capacity of 14.4. It's incredibly high, but its melting point is like almost absolute 0. It's ridiculously low, right? Before you get liquid hydrogen. Yeah. So there's 0 correlation between specific heat capacity and melting point. There's just no correlation there. All right, try this one. Okay, so like I was saying, this is the trickiest that they can get because it adds one extra step in the solving for the final temperature. All right, so they tell us we're looking for final temperature, but I'm going to find that by finding the change in temperature and then doing another step after. Okay, so I'm going to solve for change in temperature. I don't know what it is. Okay, and then I'm going to write down my other givens, which is that I have a block of iron that's got a mass of 185 grams. Okay, so since it's iron, it's 0.460 joules per gram degree Celsius, and it's using 200 joules worth of energy. Okay, so E equals mc delta T. Now I know I want to find final temperature, but final temperature isn't in this formula. Could I put it in? Sure, I could go m times c times in brackets TF minus Ti if I wanted to. Okay, sure I could do that, but I just find that confuses people if I change the formula, so I'm just going to do that after. Okay, so I'm going to find what delta T is. So to do that, I'm going to divide both sides by m times c. Okay, and that'll solve for delta T. So we'll have 200 joules divided by 185 grams times 0.460, right? Okay, joules per gram degree Celsius. Okay, so when we do that, we'll find the change in temperature. Okay, so 200 divided by 185 times 0.46. Okay, so we're getting that the change in temperature is 2.35 degrees Celsius. All right, so that's my change. My initial temperature was 7 degrees. So what's my final temperature? 9.35, right? It warmed up. I warmed it up from 7 to something else, just looking back at the context of the question. All right, so my final answer would be 9.35 degrees Celsius. Jake, question? Absolutely. Okay, so if I did that other manipulation, okay, I would get 200. I would actually have to do, so I go 200 divided by 185 times 0.46, end bracket, and then, whoop, I missed the bracket there. And then I would go plus 7, okay, 9.35. Yep. Okay, any other questions on that one? Everyone's good with that? I mean, because essentially we did the same thing, right, Jake? I just did it in my head afterwards. Wasn't, yeah. Yes, but the only way you would get a negative number is if you used a negative energy, right? So if the question said an object is cooled, you know, from this temperature to this temperature, you get a negative temperature change, then you would get a negative energy as a result. Okay, I don't remember the last time I asked one like that. Okay, so on the or in the booklet here, after this page is where these other questions can be found. Okay, so they're just some specific heat capacity questions. The first like 3 or 4 are asking, actually the first 5 are asking you to solve for C. Then there's another 5 that ask you to solve for E. So what I would do is like do number 1, do number 6, do number 11, right? And then go back and do 2. That way you're not doing 5 in a row that are exactly the same. Okay, I should have just randomized it, but I didn't. All right, so give you guys a little bit of time to work on that. I would say probably call it up on your phone because otherwise we'll be moving this around all over the place.